Yeah, good morning. We were looking at an important system in our vehicle, that is brake system, and its performance is what we are looking at. And we look at not as an understanding or looking at the brake system and the design working principle. We are not looking at like that. Rather, we are looking at the braking performance of a whole vehicle and how the vehicle braking performance is quantified. So when I say it is quantified, how quickly the braking action can take place and can be stopped in the shortest distance without any skidding of your vehicle. When I say skidding of your vehicle, without any skidding of your vehicle, means it is safe braking. So safe braking is what we were looking at, and the safe braking can be achieved with the help of modern control system, such as an anti-lock brake system. When you look at the word anti-lock brake system, the lock word says, so the tire should not get locked during braking. I should brake my vehicle, and the vehicle braking should be very much effective. The efficiency of braking should be good enough so that the vehicle would stop safely without locking any particular wheels out of the number of wheels in the vehicle, right? So all of them should stop simultaneously, and that would be the preferred condition for safe braking. When I say braking, it is not jamming on the brake. It is not attempting to lock the wheels of the brake, right? It is attempting to decelerate your vehicle and stop your vehicle. That is what is safe braking that we talk on. But when then you can put a question that is that wheel not locked? What would happen? Sudden braking that I apply. Of course, that's happened when you drive on highway. You see sudden intrusion in your path. You have to suddenly apply on a brake. So you jams on the brake. So then there is a condition that the driving condition is different. Maybe the road surface what you drive may be different. At that time, your severe braking may make that the vehicle can get into a trouble, can get into an unstable state because of the only reason that the distribution of braking force and the front axle and rear axle is what is the important criterion. So the brake system, you can't have, whenever I apply a brake system, I will have the same constant braking force distribution in front and rear. So that has to get modulated. So when it has to get modulated according to the need of your driving condition, load condition, and the road surface condition, the speed of your vehicle is concerned. So there are many parameters that are important in a vehicle. And that time, the distribution of the braking force in front and rear axle has to be happened intelligently, so that I would be able to extract the maximum braking potential of my vehicle with the safe braking. So with the safe braking means sudden locking of wheels should be prevented, right? So that's what you understand, and we were looking at it. In the last class, we looked at what is the maximum braking force that can be developed by brake system in the front and the rear axle is limited by the normal loads under driving condition in front axle and rear axle, of course, on the road surface coefficient. So F max is P times WF, we have seen. FBR max, maximum braking force at the rear axle, is equal to P times WR that you have seen. And for that purpose, we looked at the free body diagram of a vehicle and looked at all the external forces and derived the expression for WF and WR under braking, and then we proceeded to get the expression for this braking force maximum values. So I'm going to continue from that same point today's lecture. I'm going to take to a interesting discussion on physics of what's happening when you apply brake and this distribution of braking. What do you mean by ideal braking and so on is what is today's class content, and that would motivate you to learn the crux of ABS system, right? Yeah. So let me share my screen for the class. Hope you are able to see the screen, and this lecture is number 40, but let's just look at what we did in the last class as this free body diagram, whatever I have briefed that you could witness and recollect, and you are with me, right? So this equation 1 gives you two forces and the tire road interaction, that is braking force and the rolling resistance. Rolling resistance 8 braking is what is witnessed in equation 1. And that is to be equal to this side all the other forces that are there. Right, and when you take your moment at the contact patch, you are able to get your load distribution in the front axle and rear axle given by equation 4 and 5, and I replace these resistances offered in your vehicle by your contact tire rod interaction contact forces. And this 4 and 5 are an important equation because that and the road surface MEP value and this load is what is deciding your maximum braking force that is possible. If you look at in particular for the front axle is this and for the rear axle is this. And we concluded our lecture looking at this important condition called an ideal braking force distribution, and that would be achieved when I have my ratios of FB max by FBR is same as that of the load distribution in the front and the rear axle during that condition. That is why I just to take these ratios here and I just reduce it. So in this case, it appears that I cancel this MEP, W, and so it's a common factor I cancel, but this W is what is going to decide your L1, L2 distances. Maybe this H can be constant from the road surface for the CG vehicle when loading condition or unloading condition. But when it is loading condition, the distribution requirement would be different, and unloading condition, the distribution requirement is different. So you should not misunderstand that since this factor goes off, and this distribution of braking force proportion in front axle and rear axle of the total braking force available is dictated by this factors which are in bracket, where they are essentially the geometry L1, L2 and the CG location height and coefficient of rolling resistance and road elevation coefficient. So you cannot conclude that they depend only on the vehicle design and the road surface. Importantly, it depends on the load of your vehicle. That is very important. So today's class will understand when it is a fully loaded vehicle, what is the requirement of distribution of braking force for an ideal condition like this, or if it is unloaded vehicle, what is that? So that is why, though mathematically we cancel this, we cannot conclude that it is independent of load. It is primarily depends upon what is the load acting on your vehicle and its distribution, right? So that is to be kept in mind, and we were looking at this definition. So if you are asked in examination or any time, what do you mean by ideal braking force distribution? What is that you have to say is, ideal braking force distribution is that under a particular given road surface MEP. So for a given road surface MEP, I decide this road surface, right? And for a given loading condition W, if my brake system supplies the maximum braking force that can be supported by the road surface in this fashion, then I would be able to have my ideal braking distribution, because that would make all the wheels going to decelerate at the same rate and stop. So it prevents locking of wheels suddenly. That is what is an ideal braking force distribution, and also it is going to give you maximum braking efficiency possible. Maximum braking efficiency that's possible. So when I say maximum braking efficiency, what do you mean by that? All is what today's class we are going to revisit and look at it, right? So the case study vehicle light truck in the last class we looked at, maybe this light truck is of 10,000 pounds fully loaded condition, the gross weight of this vehicle, and that 68% of the load is in the rear axle. The static condition given dictates these values, and we substituted in this formula 8, and then we got this ratio 47/53. So what do you understand from this ratio is now 47% of the total braking force should act at the front axle, and 53% of that should be on the rear axle. If that is so, then the braking would be ideal braking force distribution. So we just to say this, but now the question comes in your mind is, how can I tell that quantitatively? How can I have that through a formula is what is the question mark now. So today's class we are going to deal with that only. And before that, let me just again bring in that an important point. There are two cases that we have looked at, that in case of this distribution, 47% and 53% is not achieved, what would happen? If my front axle, front wheel braking force distribution is less than 47% and this is more than 53%, what would happen? And that time you would have the rear wheels would lock, right? Rear wheel would lock. When rear wheel lock, what do you mean by rear wheel locking before the front wheel lock is? So instead of saying locking, it is approaching to lock. Rear wheel approach locking before the front wheel lock. That means the rear wheel lock scenario would make the vehicle is unable to resist the lateral force that can be that is acting on the vehicle. So that would create an unstable state of your vehicle. It is going to have some yaw displacement suddenly, and it can spin about this vertical axis, right? So that's what we have seen. On one hand, if rear wheel lock approach before front wheel lock and it locked, then your vehicle cannot withstand for a side force, even the smallest is acting, and driver cannot have steering control, and the vehicle will go an unstable state. On the other hand, if you look at the distribution is such that the front wheel lock before the rear wheel lock, then what would happen? You would see that the yaw center of this change, which is in front axle acting, would get shifted to the rear axle. And the front wheel axle cannot support the necessary or cannot resist the side force acting, and then this will go. And the inertia force acting at this CG location would create a self-correcting couple, yaw couple, and that would assist, that would try to bring the vehicle in straight. And also there would be, of course, the loss of steering control momently happen, but the driver can immediately react. And he can either fully unbraking or partially reducing the braking force, and he can bring the vehicle in control. The stability is not a question mark in the second case. So this is what we have understood from last class. But that question now is, how will you determine the condition under which the front tires are going to lock or rear tires are going to lock? Because I say that if this happens, that like that. But now the question comes in your mind, how can we say through some quantitative way, through some formulae? So that's what we are going to look at in today's class. And this is lecture number 40. So lecture number 40. And today's date is 1/12/2021. So, how will we determine the condition under which front tires or rear tires will lock up first? Is what is that the question that I put to begin this lecture. And for that, let's look at now our equation 1, what we did in the last class. So this equation 1, what we have got it in the last class. So that gives you the sum of the resistances equal to that of the braking force FB and RR. So this expression I am going to consider for the easiness of looking at this approach. The other resistances, aerodynamic resistance, I am not going to consider. Anyhow, I am going to apply brake and then the speed reduces. So the locking will be in a smaller speeds, right? So we can neglect this RA, RD, and this I'm considering my vehicle on a level road and apply. So for the sake of easiness, but in a real time you have to account them as well and go ahead of doing this. So for today's particular class, let us not account these three factors, and we'll only have equation 1 where FB plus RR equals WA by G. So I'm going to start with that equation. So let's look at now the condition of the braking force FB plus the rolling resistance R is essentially to overcome this WA by G. So WA by G is what is an inertia force that we looked at in our D'Alembert's equation. If I write like this, these two forces acting at the tire rod interaction gives me the necessary braking force. So then it becomes an effect force. WA by G is what is needed for braking my vehicle. So this is my equation. I'm going to consider, and from this let me rewrite what is my braking force to be given from the brake system. So from the brake system, what is that braking force that I get should be for these two, right? It has to be equivalent to this. So I take this rolling resistance, because rolling resistance is because of tire property that is there in your contact patch. It is not supplied by brake system. So brake system force is equal to this, is what is my first equation in today's class. And we know already we derived the normal loads WF and WR in the last class. So let me take now WF without considering rolling resistance, without considering aerodynamic resistance, other thing, according to equation written here. So for that way, my WF is going to be now WL2 by L. This is static component, and its dynamic component is only given by H by L into WA by G. So I do not consider the remaining terms. I only take this term, and in this W by L is common. So let me take W by L out, and then I'll have inside it is L2 plus HA by G. So this is equation 2. So in this H is the CG location, height from the road surface of the vehicle. And this A is what is your deceleration in meter per second square. And it's divided by G, so that I'll have my A by G is deceleration in terms of G units, right? So now the normal load is expressed now with this, which is having its static component as well as its dynamic distribution. So this is equation 2, and my normal load at the rear axle is WL1 by L minus H by L into WA by G. So this minus sign to be noted here, because the same amount goes in front during braking. We feel that no load is going transferred in the front, and the same amount is subtracted from this, and that's going to be W by L into L1 minus HA by G. So this is my equation number 3. So now, now let us define the braking force from the front and the rear axle supplied from the brake system is FB. So this is total braking force here, whatever that I have. So if it is for FBF in the front axle alone, that would be this total braking force times that fraction of the distribution proportion. So that proportion is what I call it as by KB. So KB here is what is in the last class itself we defined. So KBF is defining the proportion of braking force out of total braking force is distributed in the front axle. So that is this KBF. So this into what is that? The total braking force FB is what is the FBF that comes from brake system. That's come from brake system. So this is going to be now equal to KBF. In this FB here is what is that? Already I have it. I have written here. So that's going to be WA by G, and RR is FR into W, where FR is rolling resistance coefficient. That's already you know. So let's call this equation number 4, and the next equation is now I'm going to write it for the rear axle distribution. So FBR is going to be KBR I'll call. So the KBR is nothing but 1 minus KBF, because it's proportion. So KBR plus KBF is 100%, or it's 1. So I can rewrite this 1 minus this like that. So let me put that here, KBR into FB, or it is 1 minus KBF into FB. So FB here is this W A by G minus FR into W. So this is my equation number 5. So having this number of equations written, you understood clearly these equations. Now let us go for case by case. So what is that? If the front tires approach lockup, what will happen? Correct? If the front tires approach. Look at approach word. Approach means it's not locking. It is impending to lock. It is approach lockup. Then, correct? When it is going to happen? Lockup. When it is going to happen? Is this what we are going to look at? When you have the maximum, this force MBF is happened to be of maximum possible force that is dictated by road surface as well as the load in the front axle. So when FBF is equal to mu P times WF, mu P times WF, right? So now I have WF by equation 2 and I have my FBF from equation 4. So I can substitute that in this and my equation is going to be further developed. So my equation 4, I have it here, that's on my left hand side. So that's KBF into WA by G minus FRW. On the other side, it is mu P times WF. So WF here I have, that is W by L, W by L into L2 plus HA by G, right? So now in this again, you see, I have W common both sides, so I can just remove that for simplicity now. And I can look at now the expression for A by G. So in this, what is A by G? So this A by G is deceleration of vehicle. It's not wheels, it is deceleration associated or deceleration of vehicle associated with front wheel tire impending to lock. We should say that way. Deceleration associated with deceleration of vehicle associated with impending lockup of the front tires. Impending lockup. Impending lockup means there is a boundary value, boundary. So it is not touching that, it is just going closer to it. Impending lockup of front tires. So similarly, if I have my expression for FBR that's dictated by MP times WR, I would have a deceleration of a vehicle associated with the impending lockup of my rear tires. If these two are equal, then it is ideal braking force distribution, to say in an easy way to follow. But it is not so. So one will be smaller than the other. Whichever is smaller, that is going to first dictate locking up, or that's going to experience lockup before the other one. So that is what is the crux. So now let's now get this expression of A by G out of this equation written. So I have A by G on both the side. So I have to bring it on one side. So let me do that simple manipulation. So here on my left hand side, I have KBF A by G. And on right hand side, I have here it is, right? It is mu P H by L into A by G. So if I bring it there, this minus on this side, and it is going to be mu P H by L into A by G. That's equal to, on the other side, I will take this minus FR into KBF become plus, and here I have mu P L2 by mu P L2 by L plus FR KBF on this side. So now I can write the expression of A by G. A by G associated deceleration associated with the impending of front wheel lock. That's going to be, on this side I have this mu p L2 by L plus F R KBF by KBF minus mu H by L. So this is an important equation. So let's call this equation. So let's call this equation 6, and that equation lead to equation 7. Right. So I have got now the expression for a deceleration of vehicle associated with the front wheel lockup experiencing impending of locking up of front wheels. Similarly, I can get A by G R. So how do I get? Then it will be FBR, that should be equal to mu P times WR. So I can rewrite the same way the expression, and I can derive this. So I will have here FBR is 1 minus KBF. I'm going to have only KBF as one variable appearing in both the equation. That's why instead of writing KBR, I take it 1 minus KBF into FB. So here FB is what? W A by G minus FR into W. On the other side, it is mu P times WR. So WR would have my static components, that's WL1 by L minus HA by G. WHA by G. WHA by G. Right? That is the expression here. We have it here. So yeah, so W by L taken out. So if I take it WL1 by L plus WHA by G, that's correct. So this is what on this side. So now again I can write an expression in this. So looking in this, so I as I have stated here, A by G in this equation, I'll put here subscript F. So similarly now A by G R. So it is deceleration in G units, right? That's why we divide by G associated with rear wheel tires impending to lockup. This is the deceleration. So now let us get that expression by doing the similar way. How did we get equation 7? I will have A by G. I'm writing the final one. That's going to be equal to what is that I'll have now? Mu P L1 by L plus, here I have KBF, instead I will have 1 minus KBF. So it is FR into 1 minus KBF divided by KBF, 1 minus KBF. And here I have minus sign, that sign would become plus in this case, plus mu H by mu PH by L. Right? So this is my equation 8 and equation 9. Right. So now I can write the conclusion that if I have my this again look at in this expression, you have 1 mu p. So it is for a given road surface. If the road surface is not of known mu p value, I have on my right side wheel mu p is different and left side wheel mu p is different, then it is different. This formula cannot hold good. So we make the simplified assumption to have an approach. How will we look at this wheel locking approaches or the maximum possible braking efficiency and all to see on a given mu value, right? So in this juncture, let me just tell you what is the braking efficiency for a given MEP, for a given MEP. So for a given MEP, what is that you say braking efficiency? How much is this A by G deceleration is achievable for the given MEP? Is what is defining your braking efficiency for the given MEP surface. So if MEP surface is very small, then it will be dictated there. So that condition here can be like this. So when I say this MEP, it is not always so you have this MEP value can be 0.8 or 0.85 for a good 0.85 or 0.9 for a good asphalt dry road surface. But on this the same time, you can also have road surface when it is greased. Suppose it can change into 0.3, 0.2. And if it is of icy surface, you see in European countries, all it's very cold, and the road surface is enveloped with an icy fog. So at that time, the surface mu would be different. So environmental condition would change the road surface nature. So at that time, for the given value of this, how much is deceleration is achievable is what is referring to braking efficiency, right? Braking efficiency. If A by G achievable is less than mu P is always you consider, then you define like that. But it is not necessarily like that. A by G achievable can be more than that, this also. But when A by G is less than mu P achievable is there. That is how the road surface is there. And if this happens to be smaller, then your efficiency is defined like that. Braking efficiency is defined like that, right? Why? Because if you look at the racing car on the test track, you see this A by G value is not going to be a fraction. You say 3G, 4G acceleration, they say. At that time, you may have a question mark. If the road surface is at the max, say 1, or it can be slightly smaller than 1. And then how efficiency of braking that you are dictating. So that's not so. When the achievable braking efficiency, deceleration happens to be smaller than that, then I define my braking efficiency is dictated in this fashion, right? That has to be remembered carefully. If you read the Wong textbook, every word is important. If you miss out one word and you are trying to look at equation only, you will misunderstand things. So please understand here this point. Now let me write this and discuss further. So what is it? If I have this equation 7 and 9 now, in that if I have my A by G F is less than A by G achievable at the rear axle, then the front wheel lock up first, then the front wheels lock up first before the rear wheels. On the other hand, if A by G R is smaller than A by G F, obtained from these expressions 9 and 7 respectively for the second case, and you get this, then the rear wheels lock up first. So if you have to get all the wheels to go together, and then you are able to achieve this maximum efficiency, right? All the wheels go together means what? If, third case, if A by G F is equal to A by G R, then that refers to if my deceleration developed, even it is less than whatever the MEP value, but it is maximum achievable deceleration rate, then the efficiency of braking act 100%. That means what? The braking distance would be shortest distance possible, and it is safe braking. All the wheels would go together and stop, unlock, right? Decelerate together. So that is what is the meaning. So this A by G written is at the vehicle level, and we are looking at like that. And here to say this 100% is why I have put it. So then what is that I mean to say? What is that maximum deceleration achievable? That's what is the meaning. So when I say A by G is less than μp, that is what is going to dictate your braking efficiency in this fashion. Then the maximum braking or maximum deceleration achievable, that means A by G achievable is equal to μp, right? That's what you have to understand. So to understand this all, so you may ask a question, do you have any doubt here in the statements I have written? I have written this statement here. Looking at equation 7 and 9, I am writing down this. So this equation 7 and 9 expected to be equal for maximum potential braking capability of the vehicle brake system to extract during braking, right? And it can happen that this can be differing like that. In such cases, you will have either front wheel lock first or rear wheel lock first. So what is preferred in case it is not avoidable? This is okay. Why? Because it is only the directional loss, but driver can get alerted and he can reduce the braking force and try to change the distribution of braking in front and rear axle, and hence he can have his vehicle stable state. Of course, it has been assisted by correcting yaw couple, yaw moment. That's what we discussed in the last class. Whereas on this is not preferred. Why? Because if this happens, what will happen? Your rear axle cannot support the necessary side force that is acting, and that will drift out, and your vehicle will turn into the disturbance side. And it is you can understand in lateral dynamics what you studied, oversteer effect that would be imposed on your vehicle, and your vehicle would spin, your vehicle would go unstable state, and the steering control is lost. The driver cannot do counter steer exercise in that, and nothing is possible, and the vehicle will become suddenly an unstable state. And this is what is your ideal braking condition. So this is what you have understood. So now, when I say this is smaller than this, how that I would say is, if I express now if I look at again this equation 7 and 9, I have my deceleration achievable on one side, and the other side I have my proportion of braking force in the front axle. So if I have the plot between A by G achievable and KBF on x-axis, I would have this plot of 7 equation and the plot of 9 equation goes in this fashion. So that's what I'm going to draw now, right? So what am I going to do? I'm going to plot now a very interesting thing here. So A by G deceleration are associated with my vehicle because of braking action, and on this I am taking KBF. What is the proportion of braking force of the total brake force that comes from the brake system onto my front axle? So if I take this, and then if I have to look at my variation of this, so let us look at now what would be this value here. So this all again I'm doing it consciously for a given road surface μp. Let's consider a case study vehicle on a surface 0.85. 0.85. This is given. So on this road surface, so all the wheels are running on this same UP value. That's what I consider. In that, I have now. So what is this KBF defined here? We also know this KBF is defined as it is FBF by total FB, right? So that is what is this KBF. So this also you are now knowing it. So I have my equation 7 and 9, and I would be plotting that. If I plot that, say here I take it in this scale 0.5, 0.6, 0.7, 0.8, 0.9, and so on. So here 0.8 is here and 0.9. So this is 0.85. 0.85. So 0.85 is what is maximum deceleration achievable from the definition of NB for the given A by G by mu p ratio. So when it happens that the mu p value is smaller than that of A by G value achievable is smaller than that of mu p, then this definition holds good. Right? Okay. So here, so what is that maximum possible potential on this road surface is dictated now when I have my deceleration rate here. Right? So this is deceleration rate. So now the plot goes like that. So I have a plot that goes one like this. Another one plot will be coming like this if I do. Let me take it like this. So you understand this, this is a O, this point is A, and this point is B, I call it. So now this line is the plot by equation number 9, right? So let me have on my horizontal axis the distribution of braking force, 0, 20, and here it is 40, 60, 80, right, 80. So let me just correct accordingly, because I just want to have a particular case study vehicle of the light truck what we have looked at. So this graph would go in this way. This graph would go this way if I plot with an exact values, somewhat like this. So this is B, and here it is like that up to 100%, right? This is 100%. So 100% means full braking force goes on that. That doesn't happen, right? So you'll have some distribution. So if I look at this point here, and if I project it down now, and I would say this value is 47%. That immediately should connect to that vehicle what we have looked at in the last class, fully loaded vehicle of weight 10,000 pounds, so which is equivalent to 44.4 kilonewton, right? Is what is W. In that you had 68% of the load is distributed where 68% is distributed on the rear of W is on rear given. Then you had your KBF by KBR ratio as 47 by 53. So this 47 by 53 is an ideal braking force distribution. At that time, I would have for fully loaded vehicle. So this is full load condition. Full load vehicle. Gross load of the vehicle is full. So if I remove the load, then the weight of that is 6,000 pound. At that time, the distribution WF and WR would be different again. So that's what you should understand. It is not same proportion when I load or when I unload. So that is what is dictating. So you have to carefully handle this influence of load on the vehicle. So this is a full load condition. I have it like this. And I have this OA graph giving me the boundary of rear wheel lock, expected rear wheel lock. So if my deceleration achieved is below this line or touching this line, that is impending of locking of rear wheel lock impending condition. This is front wheel lock impending condition. So if I have my value less than 47, I was telling that here. So when I have here less than 47%, what would happen? If I put this line up, right, I would have, this is first achievable. So if I extend this graph, it will go like that. So this is what is happening. So I would have my deceleration here, A by G, associated with the rear wheel lock expected is smaller than that of front wheel lock. So in the textbook, you will not have these portions. They are trimmed. So it is only maximum possible. There's no point in discussing on it because maximum achievable is only this 0.85 for this particular case. So this plot would be varying according to this mu p on a road surface, right? So the maximum achievable, if it is a 0.6, then accordingly your distribution, this curve would be varying, and that would be my intersection point of these two graphs. That is how you should look at it. So if I have any value in denominator less than 47, that lead to rear wheel lock first approaching than the front wheel lock, which is not preferred condition. And moreover, you see the deceleration, associated deceleration at that time would be something 0.75. So if I have 40%, then here, this is what is the deceleration achievable just before the wheel lockup. This line giving me the boundary, the caution, impending state. So just before the wheel lockup, the deceleration associated is not of 0.85 to have 100% efficiency, but it is very less compared to that. That's why the distribution is very important, right? Braking force distribution. On the other hand, if I have my denominator is 47, numerator is 53, what will happen? I will have here, and that line, if I extend, that would intersect with this boundary, and that shows the corresponding deceleration and so on. So that is how it varies. So these two graphs on this are coming from equations 9 and 7 respectively. So equations 9 gives me the graph OA, and equation 7 gives me the graph AB. Right. So what will happen if I have my vehicle load is part of unloaded vehicle, right? Unloaded vehicle. Say then it is W is what is 6,000 pounds of the vehicle consider, that is equivalent to 26.7 kilo Newton, and I would have my distribution would be here based on this, it's different, right? I would have when the front is more than the rear, the distribution is different, right? In loaded condition, the distribution is this, and then unloaded condition, the distribution is WF is say in this 15.8 kilonewton in front, and WR is 11.1 kilonewton in the front. So if this is a scenario, my graph, this RWL, rear wheel lockup equation would now get changed in this way. Just it will be concentric, it will be shifted like this. And again, it will get shifted to the maximum possible thing, because the road surface where it is running is constant MEP that we consider. And then your this one would change it something like this, right? It will go like this. So now you see whether it's fully loaded condition or unloaded condition. If I have to look at compromise, and my vehicle maximum achievable deceleration is reduces to 0.6 instead of 0.85. At that time, my braking efficiency would be, that means what? I have to have corresponding braking force distribution. So if I have my braking force distribution corresponding to this, some 60 plus value, 67% something here. So for 67% here or 70%, I think so. So if this is that, then corresponding value of my deceleration is 0.6. My efficiency drops down. So 0.6 by 0.85 is what is that corresponding efficiency, which is less than 100%. where it is accommodating both loading and unloading condition. Also, if at all this intersect this line here, this point is what is front wheel lock. So that is again ensuring a stable state of your vehicle, even there is some side force acting. So this is what is that you understand for the same given vehicle. If fully loaded, what is the scenario? If it is unloaded, what is the scenario? So if I have partial loading, what will happen? This equation would be shifting. This curve will be shifting between this and between this and this. So accordingly, you will have this. So it has become very complex now. Correct. Every time we do not have the same scenario of my vehicle load, vehicle driving condition, and the road surface. Right. But to understand what is happening with your vehicle and the significance of distribution of braking force, I have chosen this case study and we look at it. So this is what this case study vehicle here is, a light truck. So the loading and unloading state, if you look at, there are 4,000 pounds difference, but that is not going to be the case with your passenger car. In the passenger car, fully loaded condition is the addition of say 4 passengers, whereas in unloaded condition it's only driver alone. So the loading capacity of your passenger car is limited compared to that of a light truck. At that time, you'll see that these graphs would become very closer, right? So let me draw a similar plot for a passenger car down now, and with that we will stop, right? So if I take instead this is a passenger car, I would have these graphs would come closer like this. Come closer like this, and this difference, if you look at it, it will be just 5% distribution only, whereas in this case, if you look at it, it will be of 25%, right? So this is how you can understand the complexity of expected performance of your brake system in order to have a maximum potential braking possible in your vehicle on a given road surface. Underline the statement, on a given road surface. If the road surface MEP values are different, it would be different. But however, if you are knowing the parameters, this equation 7 and 9 helps you to have some comment on this. So in this type of complexity to avoid, and the distribution of braking force should be such that the wheels locking to be prevented, and that is achieved by the system, by modern control system called anti-lock brake system. That's why anti-lock, it is to be prevented, locking to be prevented. At the same time, you should extract the maximum braking capability of the brake system, and the vehicle should stop safely in the shortest distance. So these are the requirement can be met by an ABS system. Is that what we will discuss on this Friday to complete our longitudinal dynamics. With that note, I'll stop today's class. If you have any doubts on these points, I would explain. Otherwise, I will stop lecturing. Any doubts on today's lecture? It was a very interesting lecture. It's very important. I know there are many students working in this racing car, other vehicle development, competition. So if you are the person working for performance of a vehicle, brake system, you have to look at, and distribution. There are many things that goes in. Of course, we looked at today for a truck and passenger car, but if you have to look at for your racing car, everything again, loading and your weight and vehicle parameters do changes, but it is of course the 2-axle vehicle, and this whatever we studied can also be looked at for racing car, right? So with that note, let me stop recording now.